안녕하세요, which means greeting and welcome to this invited sessions. I'm really excited and honored to introduce the first speaker of today. This session is Robert Jerrard. He got, in this information, he got PhD at UC Berkeley under the advice Lawrence Evans, and he got some award. His award is Ontario Premier's Research Excellence Award in 2003 competitions, and he got invited meeting professorship at the University of Pierre Marie Curie several times. And so today, I will show the today he's going to talk on Quantized title a little bit, but 70% is correct. And here, in printed here, he brought, I'm not sure about quantized vortex filament in complex scalar field. Please welcome Professor Robert Jerrard.
Let me begin by thanking the organizers for the very kind invitation to speak. It's a great honor, and also thanks for the nice introduction. So, okay, so to give an idea of what I want to talk about, let me first show, I'd like to give you a visual image. This comes from an experiment carried out with superfluid helium. And in this experiment, you'll see a movie shortly, but the point is, you can see these one-dimensional structures here and here. And when I run the movie, which is actually a video of superfluid helium, when we run the movie, we'll see these things evolving in a certain way. And so the goal of this talk is to describe one-dimensional structures in certain semilinear equations. This is an image to keep in mind. And so what one can think of is that this fluid is in principle described by a PDE in three space dimensions. And we can see the solution of the equation contains these 1D structures, which we saw moving around. And so the goal will be to make rigorous mathematical statements about these objects if possible. Okay. And so in particular, the video I just showed was a kind of a quantum fluid. Certain quantum fluids are described by, say, ideal quantum fluids are described by a complex valued wave function psi, which would solve a Schrodinger type equation. And these 1D structures we saw, a so-called vortex filament, can be extracted by looking at the solution psi. And so the vortex filament would be characterized by the fact that this complex wave function vanishes. And then also what I'll call concentration of energy, concentration of vortex. I'll define these terms later on. So for now, let's take them on a heuristic level. So the example I gave was from a Schrodinger equation, which has the nice feature that one can really see actual physical experiments showing these things. Similar phenomena occur also in superconductors, which are described by, say, elliptic or parabolic equations in different situations, or in principle by some objects called cosmic strings, which would be described by hyperbolic equations. And so in every case, one can ask the same kinds of questions, describe the one-dimensional structures, or the more generally codimension 2 structures in n-dimensional solutions of these equations. And so there are kind of common heuristics relating all of these problems. And so in particular, all of these elliptic, parabolic, hyperbolic Schrodinger equations are all related in some way to what I will call the Ginzburg-Landau free energy. I should say Ginzburg-Landau is in some way a misnomer, an ahistorical name. It's a common one, and I'll use it throughout the talk. So this Ginzburg-Landau free energy, again, here psi is still a complex valued wave function. It has two terms, a Dirichlet energy term and a term which I'll always imagine epsilon is small. And so when epsilon is small, this term penalizes the wave function in places when the modulus is far from 1. Okay, and so this has the effect of forcing the modulus to be close to 1 most of the time if the energy is not too large. And so the general heuristic is that in 3 space dimensions, this energy should be, okay, there's a logarithmic factor, but this energy should be related to the length of the vortex filaments. And so if we believe this, then in the movie on the first slide, the energy would have been in some way related to the length of the curves we saw. And moreover, we expect, again, the general vague expectation is that this correspondence between this energy, so this is a functional defined on the space of, say, H1 log wave functions. There's a natural finite energy space. This arc length functional is defined on, if you like, a space of one-dimensional curves in R3. And so in addition to this, the correspondence between these two functionals, this wave function, this geometric one, we also expect we can associate to the free energy an elliptic, a parabolic Schrodinger equation, and so on. And we can associate with this thing equations of the same type. And so the general heuristic is that the general heuristic is this, that some of these, for example, in the limit as epsilon tends to 0, we would like to see these, this sequence of functions converging in some sense to this. I've written it here in Rn for arbitrary n. And down here I have, for example, the Euler-Lagrange equation, or an L2 gradient flow, and then 2 canonical Hamiltonian flows associated to the Gisborne energy. On the right I have exactly the same things, the Euler-Lagrange equation, an L2 gradient flow, and then 2 canonical Hamiltonian equations. Here, this one just means, so in this case, the point is in the hyperbolic row here, the relationship between this functional and this thing is that the functional can be, or the equation can be thought as the Euler-Lagrange equation of the functional, in which I replace the Euclidean metric by the Minkowski metric. And over here again I have the Euler-Lagrange equation for the functional here, where I replace the Euclidean area by the Minkowski area. Okay. And then on this side I should say J is, in every case these will be codimension 2 submanifolds of a capital n-dimensional space. And so then if I have a codimension 2 submanifold, I have a natural operation of rotation by 90 degrees in the 2-dimensional normal space at each point. This is what this J indicates. I'll say this in more detail later on. Okay, and so we can summarize this in a picture. So given each of these functions, I can associate to elliptic, parabolic, etc. equations. And the strength of these red arrows indicates the sort of the state of knowledge in the different rows. And so it's quite well documented. There are numerous theorems describing the sense in which the Ginzburg-Landau energy is related to this area functional. Similarly, the elliptic and parabolic cases are very well understood. These are by now classical. The hyperbolic case has a few results rather recent, and the Schrodinger case is largely unknown. And so this is and so my goal is to give a general overview. I want to rather quickly go over the classical results in these, and then spend a bit more time on especially on the most difficult and open Schrodinger case. Okay, so to be a bit more precise, I said I expect we want to see correspondence between these two things. What does correspondence mean? So it may mean, in every case I can consider, for example, a sequence of solutions of the PDE with epsilon tending to 0, and ask what happens in the limit. And so correspondence may mean that I'll define on the next slide, I think, vorticity and energy. These are well-defined quantities. But it may mean that the vorticity of the wave function concentrates around a solution to the corresponding geometric problem, or similarly the energy concentrates around a solution, or heuristically, most level sets of the wave function are either trivial, say, or close to the solution to the geometric problem. So again, there are many results, as I said earlier, about elliptic and parabolic problems, and about the convergence of functionals there, and then there are fewer in these cases. One feature of let me say down here, there are a lot of related questions. One can consider the same, or one can consider most of the same questions about where one asks for relations between scalar equations and hypersurfaces. And so these would be governed by the codimension 1 area functional, for example. Here, the only difference is that the Schrodinger equation doesn't exist. One can also consider various gauge theories. One can consider point vortices in 2D. a distinctive feature of the questions I'm considering compared, for example, to the scalar case, is that in this complex, case on which I'll concentrate, there are very poor spectral estimates making linearization difficult. And so very few theorems have been proved by linearization techniques. Whereas down here, for example, a lot is known, and there are many of these use, for example, the Lyapunov-Schmidt reduction or related arguments, which rely on good spectral control of certain linearized operators. I should say, Junsheng Wei, who will be speaking later in this session, has been a major contributor to these results. Okay, and so next to define these quantities. So the energy density is simply the quantity we showed before that appeared in the integrand. And so this Dirichlet term plus a penalization term which forces the modulus to be close to 1 when epsilon is small. The vorticity is a more interesting quantity, if you like. And so let me define this first in R3. So I have a complex value wave function. Let me write psi1 and psi2 for the real and imaginary parts of this wave function respectively. In this case, we can define in R3 we can define the vorticity vector field to be the cross product of the gradient of psi1 and the gradient of psi2. And so if you think about it, it follows immediately from the definition that the vorticity vector field is always parallel to the level sets of the complex value function psi. And so in particular then vortex lines, which I could define to be integral curves of the vorticity vector field, will be exactly level sets of the function psi. And so the picture one has, which is in some way borne out by results, is that in these 1D filaments, in which I'm interested, these vortex filaments consist of clusters of level sets. If the energy is, again, not too big, then psi has modulus 1 most of the time. There will, however, say, be regions where the modulus is close to 0. And so if I consider, say, some value in the complex plane within the bowl of radius 1/2, and I look at the corresponding inverse image, these things should be clustered in a small set. And so in this way, and so this is a picture of how one imagines the vorticity, this cluster of level curves occupying a small set. And so the vorticity naturally has kind of a one-dimensional structure, or a slightly thickened one-dimensional structure. More generally, in higher dimensions, it's natural to define the vorticity 2 form instead, which would be d psi1 with d psi2, which is just the pullback by psi of the area form. And then similar considerations will tell us that the say vortex submanifolds, which one can associate with this a distribution of n-2 planes in R capital N. Vortex submanifold will be integral submanifolds of this distribution. And these will again be level sets of psi. And so some analog of this is true in higher dimensions. Let me say here, these little blobs are supposed to represent. I've said that the modulus should be close to 1 most of the time. There may be places where the modulus drops down away from 1, in which there could be spurious pieces of vorticity. In other words, things like this, which could. And the point is that these things are likely to be present, but there will be small and weak norms. And so in many cases, one can ignore these things. This extra junk here. Okay. So recurring issues in this family of problems is that one is that the submanifold may be similar, maybe singular. I've drawn here on the right a typical mechanism for singularity formation in the evolution equations, say for curves in R3. And so I might have a curve which starts out being connected and at some point develops a self-intersection, which would be a typical singularity. I should say that in this situation, one expects lack of uniqueness. There are two possible scenarios. Either it can disconnect itself in this fashion, or it can pass through itself like this. And so, of course, so this is an example of singular behavior for the submanifold gamma. And this would be, say, a generic solution of any of the geometric evolution equations I described earlier. Of course, establishing a relationship, the kind of correspondence I want between a PD and a geometric form will be harder in the presence of singularities. Another issue is that clearly one expects weaker estimates for wave equations and for Schrodinger equations than for parabolic and elliptic equations, where one has all the machinery of elliptic and parabolic regularity to appeal to. And this is the point I would like to emphasize. Geometric measure theory provides a useful framework for two reasons. One is if one wants global descriptions of the connection between the PDE and these things gamma in the presence of singularities, one needs a description of solutions that's valid beyond the onset of singularities. And so geometric measure theory, first of all, provides a notion of weak solution, a robust notion weak solution of geometric problems which can be used to carry this out. This has been more successful in the elliptic and parabolic cases. In the other cases, it's far too hard to prove anything beyond the onset of similarities. Secondly, as I'll argue in a second, there are what I'll call structural affinities between geometric measure theory formulations of weak solutions of the problems I'm considering and the equations I'm considering. And so what I mean is this. Let's return to the previous picture. I've added a basement to it. And so this is the picture we had before. I'd like to imagine down here in the basement is another level. And so what I mean is, for example, in the elliptic case, I can associate to a solution that begins with, and so later on I'll show in detail what these things I call balance laws are. But via Noether's theorem, for example, I can associate to a solution of the elliptic PDE a family of balance laws, which would describe various conserved quantities in integral form. I can do the same thing for minimal surfaces. I can associate balance laws. And the minimal surface balance laws, and so here this is exactly the statement that the divergence of some energy momentum tensor is equal to 0. This is the same thing, the divergence of a different energy momentum tensor is equal to 0. But the point is that on the geometric side, these balance laws form the basis for geometric measure theory definitions of these weak solutions, at least in the two cases where this has been carried out in some detail. I should say the hyperbolic case is in some way exactly like the elliptic case, except that one changes the Euclidean metric to the Minkowski metric throughout. And then, well, in every case, so in the parabolic case, what I call balance laws, we'll see are some laws governing the flux of energy. On the geometric side, there are similar laws, which are the basis for the definition of a Brachii flow. Again, the kind of a standard definition of a weak solution of the geometric evolution equation. Okay, and so, and the point is that if you look at it, there's an obvious structural similarity between these things. And the hope is that one can somehow exploit this to prove things. Okay, and again, we have the red arrows of decreasing strength indicating the decreasing strength of results as we move down in these pictures. Okay, and so what I would like to do next is to quickly review the elliptic and parabolic cases, which, as I emphasize, are by now quite classical. And what I'll really do is just display the balance law, so you can see the structural similarity I've emphasized, and then state some results very quickly with very little discussion. Yeah, here's a more simple version of the same picture, less cluttered. Okay, so in the elliptic case, and again, this is really just the, if you like, the statement that so here, if psi is the solution of the elliptic Ginzburg-Landau equation in an n-dimensional domain, and this is really just the statement that the divergence of an energy momentum tensor vanishes. I've written this in a sort of a funny way to emphasize the parallel structure between these two things. And here too, this is the statement that the divergence of an energy momentum tensor associated with minimal surface vanishes. This is also really the statement that the distributional mean curvature is equal to 0. Okay, and so again, as I said before, this is the basis for a definition of a stationary varifold. To define a stationary varifold, one just writes down the same identity in a kind of bigger class of objects. Roughly speaking, the largest class of objects in which this identity makes sense. And I won't go into any details. And I would just like to appreciate the structural similarities. And so if we believe that this corresponds to this, we'd like to believe that the energy density somehow is concentrating around an n-2 dimensional surface, and that this quadratic tensor in the gradients looks like projection onto the normal space. Right, so this P perp is the projection onto the two-dimensional normalization surface. Okay, and then some results quickly are, if I have a sequence of solutions to the equation, so I've written here are the end of a long sequence of developments that took about 10 or 12 years and occupied many people, who I've displayed below. If I have a sequence of solutions to the elliptic equation that satisfy merely, say, the natural energy bound, then after passing through subsequence, for example, for energy minimizing sequences, this is an earlier result. If I have energy minimizers, they would correspond. The vorticity would converge to an area minimizing integral current. Okay, so this is a convergence on the level of functionals. This is related to what's called gamma convergence, if you like. More generally, if I only assume a sequence of solutions and I only assume energy bounds, then energy and vorticity concentrate around a weakly minimal surface. So a minimal surface in the sense of the definition of varifold on the previous slide. And in addition, roughly speaking, one can really pass limits from the PD balance law to the geometric balance law. And then there are many further results. The contributors include, for example, one of the first results is your Riviere. Then there's work of Lin, Riviere, Sondier. In some way, the most definitive results are due to Bethuel, Brizes, Orlandi, who established, say, these ones here, and relying in some way on sort of the measure theoretic part of their argument relied on tools of Ambrosia and Soner, and they supplied the PDE part after a great deal of preliminary work by other authors. Okay, so for parallel equations, the situation is similar. So here again, we have these balanced laws, and I would just like you to appreciate the structural similarity. The second half is essentially the same as in the elliptic case, except that whereas earlier had a general vector field, here I have earlier had the gradient of a general vector field x. Here I have the second. So here I can say the gradient of a gradient vector field. In other words, the second group. Then their additional terms correspond to the dissipative part, and then I have some flux terms here. So again, we appreciate the structural similarities. And we know that and I'll comment on this identity forms the basis for this natural geometric dimension theory definition of a weak solution, the so-called Brachy flow, in which one has a kind of relaxation. But again, considering a bigger class of objects, again, roughly speaking, the biggest class of objects in which this kind of identity makes sense. And then by relaxing the equality here to a inequality in a certain way. Okay, and so some results are parallel to the elliptic case if one considers only a sequence of solutions satisfying only natural energy bounds on the initial data. Then, again, the strongest results, which are due to Bethuel, Orlandi, and Smets following a great deal of work by other authors. The strongest results would say that one has convergence globally in time to this measure theoretic weak solution of Brachy flow in arbitrary dimensions. This is after passing through subsequence. A weaker and earlier result, which is due to myself and Soner and Fong, is that for well-prepared data, if I start with data for which the energy and vorticity concentrate along a smooth submanifold, then in this situation one has convergence along the full sequence as long as the limiting flow remains smooth. And let me say a few words about the proof in this case. So, so schematically, here's the situation. We have this picture I've shown before. And in this case, we have a bit of extra information. There's a result due to Elmanen in the 90s, in the early 90s. Well, as in order, there are these structural similarities between these two balance laws. It's not clear how much to make of that at the outset. There's also a result of Elmanen, which essentially, he didn't quite say it this way, but it implies that for what you may call an enhanced Brachy flow, for a weak solution with certain additional good properties. If I have a weak solution, in other words, something satisfying the balance law, that at time 0 agrees with the smooth solution, then it continues to agree with the smooth solution until the first time when the smooth solution develops, loses smoothness. So for example, the first self-intersection as shown in the diagram. And so the way that the proof works in the well-prepared case is that one has information essentially from understanding the relationship between these two functionals. One has what I would call variational estimates that allow one to make this connection solid enough that one can, well, this is not quite true, but one can do something like this. More precisely, what we really do is this weak strong uniqueness proof involves using certain test functions in the definition of Brachy flow. And it turns out that if one uses exactly the same test functions in the definition of the energy flux over here, plus these additional variational estimates, then that suffices to show a concentration of energy and vorticity around the mean curvature. And so the point which I'll make repeatedly is that this question of weak strong uniqueness is intimately connected to this convergence question in the evolution problems. The point being that one would like to view these things, these quantities arising from say energy flux or quantities determined by a solution equation. One would like to determine these. One would like to view these as kind of approximate weak solutions in this sense, where the error in approximations arise, for example, from the fact that these are not the right kind of objects. But nonetheless, if one views these as, one can try to exploit this analogy to really prove theorems in this fashion. Okay, moving on to the hydraulic case, which again I'll skip over rather quickly. So just to give you an idea, this Minkowski mean curvature equation is what the equation says. It's the relativistic version of the equation that says acceleration is equal to mean curvature. And so here's a movie of a solution down here. This first arose in string theory, and you can see there's a wave equation oscillates as you might expect a wave equation to do. This solution is actually singular at certain times. It has I think a zero-dimensional singular set. I've arranged it to stop at a singular moment. right? So we can see here the manifold is no longer immersed. But so I want to establish, I like to show concentration of energy and vorticity in solutions to this thing around these things, at least until the first time when these singularities occur. Okay, that's the goal. And again, there are balance laws. Let me just say the balance laws are really exactly analogs of the elliptic balance laws, where one replaces the Euclidean metric throughout by the Minkowski metric. So, for example, in the on the geometric side, I've just written down the this is literally the Minkowskian analog of the Euclidean balance law, where I've replaced the Euclidean quantities by Minkowskian quantities throughout. And then I'm just introducing this notation, these energy momentum tensors for the theorem of state next. And so this again is more recent. There is one result of this which is just a few years old. And this would say, given a smooth, compact, embedded time-like codimension 2 submanifold with vanishing Minkowskian curvature, given such a thing, then there exists, say, a sequence of solutions of the Ginzburg-Landau wave equation with, if you like, so this implies, as I have said many times, this implies energy and vorticity concentration around the around gamma. And more what this does also, it gives a quantitative estimate of the extent to which the PDE balance law differs from the geometric balance law. That's what this is telling us. And of course, this is only so the weak points in this theorem, which are many, is that okay, the rate is not very good. One may be able to improve this to -1 log to -1, but it's the rate is not very good. And this is true only locally in time, and one has to choose the initial data moderately carefully for this to hold. Okay, and one should view this again, continuing to emphasize this, one should view this again as being something like a, well, let me say, in this case, there is a start toward examining this geometric problem in a geometric measurative framework. And so Bellatini, Novalga, and Orlandi a few years ago introduced the notion of what they call Lorentzian varifolds, which are exactly say, a candidate for an analog in this Minkowskian setting of the classical Euclidean notion of a stationary varifold. There actually is no weak strong uniqueness theorem yet known in this setting. Due to some, I mean, their definition is a bit difficult to work with, and that may be the weakness. But one would like to view this, yeah, let's just say, I guess in the interest of time, I'll just assert that this is that when the weak strong uniqueness theorem is found, it will mimic this proof here. So let me move on to the Schrodinger case, because this is what I really want to focus on. Okay, so the Schrodinger case, I'll spend the last part of the talk on this. And again, here's the Schrodinger equation. The corresponding geometric equation is the following. It says the velocity is the curvature, kappa, times the binormal vector. I'll show a simulation in a moment. All these simulations I show of the Schrodinger problem are based on a numerical implementation by D.D. Smets of an algorithm of Tom Butke. And I should say also, you'll notice that all of my recent results on this are joint work with D.D. Smets. And so in this case, the binormal vector in this is an ellipse sitting in the xy plane at time 0. The binormal vector will be pointing in the vertical direction. And in general, the binormal vector is sort of orthogonal to the plane that a curve, at a given point, the plane to quadratic order sits inside a plane, or the curve to quadratic order sits inside a plane. The binormal vector will be orthogonal to that plane. Okay, and so here's a simulation. The ellipse, I think, is more sharp at these ends, so it'll move it more quickly here and more slowly here, if I can see it correctly. And, right, and so this is an example of this, where the curvature is bigger, it moves more quickly, and it moves in the spiral direction. And so our goal is to establish a connection between this, and this again is still basically wide open, or quite open. Okay, and so, again, let me start by showing these balance laws. And in every case, there's this architectural similarity between these two things. And also, sort of formal computations lead one to expect that, that these quantities up here should converge to these quantities down there. A difficulty in this thing, which is that this balance law, if you like, contains both the vorticity here and quantities related to the energy over here. Whereas other things, the earlier ones had essentially only the energy. Which made them more tractable. Okay, and so so in this case, instead of stating results, I'll state a conjecture, the main conjecture, which is the main open problem in the field. And so the conjecture is that if I'm given a smooth, compact, embedded binormal curvature flow in R3 for an interval up to time capital T. Then, if you like, there exists a sequence of solutions to the Gross-Piecewise equation, such that, so this says that the vorticity concentrates around the vorticity time T of the solution psi concentrates around the curve gamma T. Similarly, energy time T after a suitable rescaling concentration around the curve gamma T. Okay, one can pose similar conjectures in arbitrary dimensions. This is hard enough, actually. This is quite hard, as far as we know. Okay, so there are some partial results, which I'll describe. And so first is that there exist, first of all, there exist translating solutions of both families of equations. There exist translating solutions of the binormal curvature flow and of the Gross-Piecewise equation. And so for certain translating binormal curvature flow, the simplest translating solution of the binormal curvature flow is just a circle, which has constant curvature and will move with constant velocity in the direction orthogonal to the plane in which it sits. Okay. So that's a translating solution. And also helixes form another family of translating solution. So corresponding to these, there are translating solutions of the Gross-Piecewise equation, which converge, whose vorticity and energy converge in the proof sense. Okay, second, and so this is, but these are basically elliptic results. These are really not dynamical results due to these authors. Secondly, roughly speaking, vorticity always concentrates around some one-dimensional red bulb curve. And so under only energy bounds on the initial data, one can at least extract a kind of limiting geometric object with a limiting object, vortex curve, with the right geometric structure in the sense of being a one-dimensional curve with tangents everywhere. And then we have various conditional results, which say, for example, the conjecture is true if I could verify that these limiting vortex curves don't lose arc length. If the arc length is constant, then the conjecture would hold. And really, what one would like is to have a kind of quantitative version of this, saying that if conditions like this are approximately true, then the conjecture approximately holds. This would suffice to prove the whole conjecture. And I should say there are quantitative versions of estimates of the sort, but let's see, say the things strong enough quantitative versions that would be needed that would suffice to conclude the whole conjecture. To establish those, the most natural way is to pass through certain other estimates, which are false. Okay, and so there are genuine obstacles to prove this. I mean, this is probably true, but the natural roots to the kind of quantitative relaxations are not true. Okay, however, the conjecture does hold if gamma naught is a circle, or more generally, a finite union of coaxial circles, with, say, in the equivariant case. And so here, I should say this. I won't say anything about this group, but in this case, we were able to circumvent some of the obstacles I briefly alluded to up here. A circle has very strong orbital stability properties, which make it rather easy to prove this. And in this case, although it doesn't look like a much harder situation, in fact, it's considerably harder, and one really has to address these difficulties, which one is able to do in this equivariant case. Okay, so this is really what's known. And I should say this this proof has two pieces. One is to say that if these conditional results, if these conditions hold, then the conjecture is true. Sorry, then a weak form of the conjecture is true. And then the second is to show that the weak form of the conjecture implies a strong form of the conjecture. So that's what's proved in these two papers, respectively. And so the second is really, again, a weak strong union theorem for a weak solution of the binormal curvature flow. And so part of the ingredient here is understanding what does this balance law, what is really its connection to the to smooth solutions. Okay, and so this motivates a study of weak solutions of the binormal curvature flow. In other words, roughly speaking, solutions who merely satisfy the balance law. Okay, and so in the remainder of the talk, I'll talk about these weak solutions of the binormal curvature flow. I've given one motivation, which is this big conjecture. The other motivation is that for example, this allows change of topology of vortex filaments. Physicists believe that this occurs. In fact, in the movie I showed in the first slide, they would argue, based on this evidence, that one can see changes of topology in vortex filaments in these experiments. And then also there are just interesting phenomena for taking English data. And so what I will show here are movies where on the so let's just show it. Well, on the right I'll have a binormal curvature flow where the initial data is a square. On the left, so if I parameterize this by arc-length, and then look at the derivatives, that's what I show on the right, are the derivatives, the unit tangents. And so this is a piecewise linear curve. This is a piecewise constant curve, where these lines join the constant values. And so the piecewise linear curve, one point to notice that the equation doesn't obviously make sense with this lack of smoothness, and yet nonetheless one can solve it numerically and get rather well-behaved solutions. Here's the tangents. So we can see that the lack of smoothness has rather dramatic consequences when we look at the tangent vectors. I should say for experts, this is what's called a one-dimensional Schrodinger map into the unit sphere S2. And one can see here, for example, that I've chosen this to stop at a time where the limiting curve looks like it's almost piecewise linear. And so there are a lot of interesting conjectures. There's a recent paper of De La Hoz and Vega in which they have numerical and say heuristic arguments with a lot of conjectures about exactly the situation of binormal curvature flow with polygonal linear data. And so they would argue, for example, that these things are piecewise constant at rational times and fractal at irrational times. That's the basic conjecture. Of course, they have certain conclusions, including they write down a kind of explicit candidate for a solution. But there's no. Sorry, I'm going backwards. Here's their evidence for fractal behavior. Okay, and so in our study of weak solutions binomial curvature flow, our strategy is, first of all, we have a definition of weak solution based only on the balance law, with some additional requirements. We require that the curve be closed, and we require that the arc-length can increase. The setting is what's called oriented variables, and so these would be, roughly speaking, again, the largest class of objects for which the definition makes sense. And so our results would be a very robust existence theory, including, for example, for polygonal curves. Extreme non-uniqueness, which one expects. Whenever one has self-intersection, there should be non-uniqueness. And there can be numerous pathologies in the setting. However, the main positive result is this weak strong uniqueness result and even a so-called stability. So this way, if I start with a rough curve, which is near a smooth curve, then it remains nearby in some sense for some time, at least as long as the smooth curve has no self-intersections. And so these fill in this weak strong uniqueness part of the diagram. Let me say they also provide estimates in weak spaces, which are in which the equation is far supercritical, and so this is of some interest potentially for that reason. Okay, and so let me quickly give an idea of the weak strong uniqueness proof. And so this is we're given a smooth solution, say little gamma, and a weak solution capital gamma. And so the smooth solution really satisfies an equation. The capital gamma satisfies only the balance laws. And I want to prove that if they agree at time zero, then they agree for later times, or more generally, if they're close to time zero, then they're close for later times, for some time interval. And so what one does is one uses the smooth solution to build what I'll call a relative excess functional, which controls the integral of this quantity here. And so this refers to this picture here. X is a point on the rough curve, and P of x would be its projection on the smooth curve, so the nearest point on the smooth curve, the nearest point projection. So this relative excess will control both the distance from the rough curve to the smooth curve, and the distance between the tangent vector at x and the tangent vector at the nearest point P of x. Okay, so and so this is if you like a kind of H1 norm of the rough curve with respect to the smooth curve. And so the hope is that one should be able to bound the growth of the relative excess. And so what we're able to do is to just differentiate and control the growth, and we can do this because we have the definition of the relative excess is rather delicate. And then there's just a computation that involves substantial cooperation between the weak solution and the smooth solution. And I know that this computation is still valid in the weak setting. So let me just conclude by saying, as I said, this stability can be seen in numerics. And so what I'll show here to finish the talk is simulations. On both sides, I simulate I superimpose two numerical results. One is an ellipse, and the other is a very small but supercritical perturbation ellipse. And so in the critical one, I've taken the ellipse in the xy plane, and I've at some point moved a segment. There's a short vertical segment out, so I've moved a point out. So it goes around and then up and then down. So we can see that would be the I can't see the green curve over here has some tangents on the North Pole and some tangents on the South Pole. All the other tangents lie on the equator, whereas the blue curve, all the tangents lie on the equator. Okay, and so the left-hand simulation is not very stable. You will not be able to see any difference between these two curves. You can't. I think that by the time such that they remain indistinguishable. If we look at it on this level, however, the point is that this is really quite a rough perturbation. Say it's well, here it is, and so the tangents of the rough curve are doing these crazy things, but all the crazy things average out to they average, and so this is really just the derivative. The curve on the right is the derivative of the curve on the left, and so all this crazy behavior averages out to be indistinguishable from the smooth solution. Okay, so this is what we can see from this is kind of a visualization of the stability results. So let me conclude here, and let me thank you for your attention.
Actually, we're now out of time, but I'd like to ask you just one quick question. Yeah.
One last talk. And notice in your GP equation you have a log x in front of dt psi.
Yeah.
If this one is removed, the solution results the same or there's some difference?
Yes, so this log epsilon factor is it's needed for the vortex curves to evolve with a velocity of order 1, and just a rescaling time. Right, and so this is true also. I should say the same conjecture is present and harder for the Euler equations. One expects the vortex flows in the incompressible order equations evolving by this binormal pressure flow. And again, logarithmic rescaling is necessary there to see the vortices evolve with unit speed.
In the video you showed at the beginning, it seemed to me that the one-dimensional structures were formed from sort of little beads on them, as if they'd coalesced from zero-dimensional structures. Do you have any comments on that?
Yeah, that's actually an artifact of the way they're visualized. And so what they do is they see the liquid helium with little tiny ice crystals of some frozen substance, which then congregate along the vortex curves. And so that's just an artifact.
Okay, we have both questions to discuss during the break. And thanks, and also congratulations for his invited speaker.